Welcome to Spring LIB.
This is the answer to Chapter 31, problem number 46 from the Smith Organic Chemistry textbook. And in this problem, we're told that in the presence of acid, 2-methylpropene oxide undergoes chain growth polymerization with nucleophilic attack occurring at the more substituted end of the epoxide. Draw a stepwise mechanism for this process and explain this regioselectivity. So I think to begin, in the epoxide chapter, we learned as a rule of epoxide reactions that under acidic conditions, nucleophilic attack is always going to take place at the more substituted carbon of the epoxide. And under basic conditions, obviously, it's exactly the opposite. So the regioselectivity that we're asked to explain is readily explained just by that rule. So when epoxide's open under acidic conditions, the nucleophile is going to attack at the more substituted carbon. Okay, so with that out of the way, we can go ahead and draw the mechanism here. And again, like many other problems have been so far in this chapter, this mechanism is sort of a throwback to an earlier chapter, and it's just an epoxide opening under acidic conditions. So we're actually told this time that it's H3O plus that we're asked to use. So rather than just drawing an H plus, I'll draw the H3O plus. So to start, the epoxide oxygen is going to grab that proton. The hydrogen-oxygen bond in the H3O plus will break. So we now have protonated the epoxide oxygen. So the oxygen has 3 bonds. Obviously, it's going to have a plus charge on it. And so now we have just water, just regular water, that can act as a nucleophile. And again, we're asked to explain the regioselectivity. So the oxygen, the water is a nucleophile. These are acidic conditions. So the nucleophile attacks at the more substituted carbon of the epoxide. And so that's what we see. This is going to open the epoxide. So the epoxide is now opened. That doesn't look so good. There we go. That looks a little better. So there's the residue of our nucleophile with a plus charge on it still. Well, not still, I guess. A plus charge on it. The oxygen now has 3 bonds. So there's more water floating around. So the oxygen of the water can grab that proton. Those electrons can revert to that oxygen. That gets us to here. And so from here, this molecule that we've just made can act as the nucleophile on another epoxide. So I'm going to just make a fresh line, a second line here. So here's another molecule of our starting epoxide. And I'm actually going to draw it protonated. We don't need to redraw the protonation mechanism. It's shown immediately above this molecule, so we can take for granted that it happens exactly the same way. Well, actually, pardon me. Yeah. So the mechanism is drawn immediately above. So this is this. So that's where we're starting from on this second line. So the molecule that we just made, as I said, can act as the nucleophile here. So this oxygen has lone pairs. It's acidic conditions. So once again, attack at the more substituted carbon. That bond breaks, opening the epoxide. And we end up here. So now, you know what? I'm going to go ahead and redraw this because it's, yes. Okay, and so now this oxygen has a positive charge on it. It has 3 bonds. Of course, once again, we will invoke a passing water molecule, as always. And so lone pair on the water oxygen is able to grab that proton. Those bond electrons revert to that oxygen, relieving the positive charge. And we get to here. And so we now have basically a dimer of our polymer, two joined monomers. But we have 2 alcohols here. Either of these can act as nucleophiles. So if this alcohol was to act as a nucleophile, it could open the next protonated epoxide, and so on and so forth. And we would end up, with an infinite chain, a polymer extending, for as many epoxides as we have. And so that's the mechanism here. Again, the regioselectivity is due, as we should have learned in an earlier chapter, due to the fact that under acidic conditions, nucleophilic attack on an epoxide is going to occur at the more substituted carbon. And so that's the answer to chapter 31, problem number 46.